Last week we spoke of summarizing a data set with a single number, such as mean, median, or mode. This week I would like to start with an example where we analyze two data sets and compare. Let's say we were going to buy a new set of tires for our car, and we had the choice between two different brands, which we'll call brand number 1 and brand number 2. On your screen you see a sample of 5 sets of tires from each brand. We have listed the amount of miles in thousands that each set of tires lasted before needing to be replaced. Taking a look at this data, and assuming that the prices of the tires are the same, do you have any preference on which tire brand you would prefer to purchase? In order to make an informed decision, we should probably look a little deeper into the data. The first thing you might have noticed is that the range of the data is the same for both brands, with the minimum and maximum data values for each brand being 10,000 miles apart. The second thing that would help us compare the data is to find the mean of each data set, or in other words, how long on average do these tires last? Calculating the sample means, represented by the symbol X bar, we see that both tire brands last 30,000 miles on average. So the question is, what's the difference between these samples? Your first instinct might have been to choose brand number 1. And usually people will say brand number 1 because it seems more consistent. You would be correct in that assumption, but we can go even further because there is a number we can calculate to describe the variability of a data set. That number is called the standard deviation. There are two formulas to calculate the standard deviation, shown on the screen here. The one on the left is referred to as the defining formula, and the one on the right is called the computational formula. They both can be utilized to calculate standard deviation, and depending on how the data is presented to you, sometimes one is easier to use than the other. While they both look confusing and very different, they are actually the same formula, just written in different ways, and we will go through an example of how to use both of them. The first formula we will use is the defining formula. The key to using this formula is to realize that you cannot just substitute in a number for x or x bar. The entire numerator is one single value that we must calculate, and that numerator is the sum of x minus x bar squared. You can see that formula here again on the left side. To do this calculation, I make a table. I start by making a column of the data values, shown over here on the left. The left half of this table is for tire brand number 1, so we're just going to look at the first 3 columns on the left. The leftmost column are my data values, and after filling in those 5 values, I would then create the second column, which are the values of x minus x bar. You can see I calculated x minus x bar for each data value that I have, with the calculation shown in red. If you remember, x bar is the sample mean, and that was 30 for both data sets. That is why I subtracted 30 from each data value, with the calculations again shown in red. That gave me values of -5, 0, 0, 0, and 5 in my second column. Next, for my third column, I want to find the values of x minus x bar squared. I can calculate those by taking the numbers from the second column and squaring them. This will give me all positive values in the third column. I then added up all the values in the third column to get 50. And that total is what I call the sum of x minus x bar squared. That sum of 50 is what I plug in to the numerator of my standard deviation formula. The standard deviation of tire brand number 1 is the square root of 50 divided by 4. The denominator of this formula is n minus 1, and I used n equal to 5 because I have 5 data values. When I complete this calculation, I do 50 divided by 4, which gives me 12.5, and then I take the square root to give myself a standard deviation of 3.54. I followed the same procedure for tire brand number 2 on the right side of the table in the 3 columns on the right. Following the similar calculations, when I took the sum of the last column, x minus x bar squared, I got a sum of 88, and that is what I plugged into the standard deviation formula. Dividing that by 4, and then taking the square root of 22, I got a result of 4.69. Standard deviations can tell us a lot about a data set, but the first thing we'll use them for is to compare the variability of data sets. Since tire brand number 2 has a higher standard deviation, we can say that there is more variability in that data, which means there is less consistency. You can think of it like the data is more spread out, or maybe a little more haphazard. As we initially thought, since tire brand number 1 has a smaller standard deviation, that data is much more consistent and does not vary from the mean as much as tire brand number 2.